So it's a pleasure to introduce our speaker today, Dravyansh Sharma. Dravi is an ideal postdoc here and at Northwestern. Dravi was a student at CMU working with Nina Balkan. Dravi works on a lot of different kind of problems in machine learning theory and especially on data-driven algorithm design, including data-driven machine learning algorithm design with just a lot of really nice work on things like hyperparameter tuning and how you sort of get a principled analysis of the design of hyperparameters for machine learning and other algorithms. It's done this in the context of things like decision tree learning and clustering and I guess graph-based learning and most recently in the context of deep networks. And Dravi got the UAI Best Student or Outstanding Student Paper Award for his work on doing hyperparameter tuning for learning decision tree learning algorithms. And anyway, today he's going to talk about provable tuning of deep learning model hyperparameters. Take it away.
Thank you. That's such a nice introduction. Yeah, you remember all the work so well. Right. So, hello everyone. Welcome to my talk. I'm going to give this exciting talk about very recent work we recently uploaded called Provable Tuning of Deep Learning Model Hyperparameters. This is joint work with Nina Balkan, my PhD advisor, and long-term colleague An Nguyen, who is also a Nguyen student, current student. So let's get started. So hyperparameter tuning is something that's most people who are, especially in applied machine learning, are extremely familiar with. And when you think about deep learning, it's so powerful. You believe it's more automated than some of the other techniques, but there is a major limitation to this automation, and that is that you need someone to. So you have these powerful algorithms, but you still need someone to actually tune hyperparameters to make those algorithms effective on any given data set. So this is a major bottleneck for true automation. And what this needs is you need expensive domain experts and engineers to do this tuning. You also need expensive compute resources to try out all the configurations of these machine learning algorithms. And with all that effort and money and things going in, the unfortunate sad part is that you just don't have any theoretical guarantees. So this is highly unprincipled. Just to give a quick meme. So there's so much money you spend, there's require manual work, and at the end you get your heuristics, but we want to move towards this direction where it can be more truly automatic and also provably good. So you can actually give some guarantee about the hyperparameters that you're selecting. Okay, so let's start with what people have used for a long time in machine learning. So there's this thing called grid search or random search, which you just take a discrete grid or even a random selection of hyperparameters, and this has several issues. Especially if there are multiple hyperparameters, this would involve a large amount of search to get anything good. It's inefficient. It's unprincipled. You don't have any guarantees. You generally don't even hope to get guarantees about the entire space. Maybe you can say something about being best over the grid that you selected or the random points you selected, but what about the entire continuous space of hyperparameters? There is no transfer across tasks. I'll elaborate on that one in a bit. And there are also provable examples in clustering and learning to branch. You can show examples of where this data-independent grids would lead to provably suboptimal hyperparameter selection. We don't have examples for this for specific case of neural networks, but it's believable that it's also the case that if you take a uniform grid, you'll end up with something which is provably suboptimal. The state of the art, there are more recent fancy techniques which people actually use in practice today. So they include Bayesian optimization, where essentially you still don't know the structure of this hyperparameter, the performance as a function of the hyperparameter, but you sort of model it as this noisy evaluation of some function. I'll talk about this in a little bit, but there are also other approaches, bandit-based approaches, and gradient-based approaches, which are also somewhat heuristic-y. And again, they don't give any satisfactory theoretical guarantees, and they don't address usually the continuous space of hyperparameters and lack this aspect of transfer across tasks. I'll go in a little more detail about this Bayesian optimization bit because that seems to be one of the more prominent approaches. But the other approaches are also have similar limitations. So one question that remains unanswered, which is a fundamental question, is that how does the performance of your model actually depend as you vary the hyperparameter? And I think we really need to answer this question first in order to hope to achieve anything principled here, right? So the short answer is we really don't understand it. So what do people do in the absence of such an understanding? You do some crude approximation. You assume your function, your behavior of your algorithm as a function of the hyperparameter is some noise evaluation of some function with some smoothness properties, which you just assume out of nowhere. At the end of the day, you will need someone to actually design these smoothness priors very specific to the application you care about and work out these noise correlations and acquisition functions and all sort of stuff. So it really is not really automated hyperparameter tuning in that sense. This functional behavior is, you really need to indirectly still understand this functional behavior in some sense, the smoothness and other properties of this functional behavior in order to actually get good hyperparameter tuning using Bayesian optimization. With that motivation, we really want to move towards answering this question: what is the actual dependence as you vary the hyperparameter? What's the actual dependence of your model's behavior as you change this hyperparameter? And we don't even know how to answer this even for a fixed data instance. In general, we want to answer this over distributions. You want to figure out the best hyperparameter distribution. But let's even start with a single instance. How does as you change the hyperparameter, how does your loss function or your utility function vary? So with that motivation, I'll go on and talk about this base formal setup which we will work with and introduce the main result that we have. Right. So instead of tuning for a single specific problem, so this is where we start capturing this transfer aspect. So instead of a single specific problem, you tune hyperparameters that generalize across a collection of related problems. In some sense, you could also apply this result to cross-validation on a single data set, but it's much more general. It allows you to do this across task learning. So you can learn a hyperparameter which works well over a collection of tasks. Concretely, you have a problem instance X. It could be, for example, a data set that you use for a particular application coming from some problem set domain. So you would have multiple data sets which are related to each other, and you acquire these data sets according to some distribution. This is a simplified assumption, which just to start off with. In other examples, we are able to lift this assumption, but as a starting point, this is an IID assumption. All your data sets are drawn IID from some problem distribution. So examples of application-specific domains could be, some academic email spam filter for Gmail. So it's like an example of a classification problem. Or maybe you have some product features and you're trying to predict, how well they will sell. If you're on Amazon, you're trying to decide which electronic products to advertise. It's kind of a regression problem, or you're using features to predict their value or something. So yeah, our result in this work will apply to both classification and regression problems. But these are examples of concrete domains which you can think of while trying to understand our model. Okay, so the other formalism is this distinction between hyperparameter and parameter, which people might already be familiar with, but just to reiterate. So again, to start off, we will focus on a single-dimensional hyperparameter. We will have interesting examples already of this. Of course, it's a natural question to ask about how to extend our results to more high-dimensional hyperparameters. There is also this model parameter space, which it should be RD. So the models are d-dimensional. Here, actually, we don't need to assume it's single-dimensional. So the difference is your hyperparameters would be fixed during training, but your model parameters will be updated during training. So that's, again, just a basic understanding of what hyperparameters and parameters are. As a concrete example, you have this deep network with L layers. You have these model weights, which are the parameters. And so what are the hyperparameters? Some examples of hyperparameters are, there is this parametric ReLU function, which is a very simple example. So instead of using a ReLU function or the vanilla ReLU function, you could you could have a family of activation functions you could choose from. That's kind of an architecture aspect of designing your neural network. So how do you set this parameter A in your ReLU parametric ReLU function? More generally, you can also interpolate any pair of activation functions using some interpolation parameter. How do you set this interpolation parameter? So these are kind of examples that we'll be able to address. These are kind of hyperparameters. There are more, but they are concrete examples of hyperparameters that we can tune using our results. So one important aspect to highlight here is just to give a picture of what sort of hyperparameters our current results we can hope to apply for. So there's a distinction between model versus optimization hyperparameters. The model hyperparameters talk about things that affect the learned final neural network. So you do your training, you get some network, and that network is a function of both your parameters and hyperparameters. So even though your hyperparameters were fixed during your training, but they will still appear in your final function. And here they impact training. So they impact the W that you finally learn as well. So examples of these are activation function parameters, kernel parameters in graph neural networks, which is another example where we are able to provide our guarantees. We want to contrast this with things like learning rate or regularization in loss functions. So these affect the training procedure. So when you're learning the W, finding the best weights is a challenging problem. People use stochastic gradient descent and or there's some variants involving hyperparameters. But these optimization algorithms is a flavor of hyperparameters that our current work does not address. I mean, that's still an interesting question. Of course, these are very relevant hyperparameters, but the nature of techniques that we develop apply only to model parameters. All right, so now that we have that distinction clear, let's start formally modeling what the neural network even does, right? So we model this function, which we call the parameter-dependent utility function. So it takes three inputs. So there is this problem instance X, your data set that you're operating on. There is this hyperparameter alpha, which could be this interpolation parameter in your activation functions, and then there's this parameter, which are the weights of the network. And ultimately, in order to do the hyperparameter tuning, you care about this utility function. So you suppose you did your training, right? You start with this network, you did your training, you find the best weights using whatever your favorite optimization algorithm, and now you can say that this is the function which captures how, as you change the hyperparameter, will your network's behavior change, right? So your network's behavior on any problem instance X, you can capture using this utility function. And the complexity of this function is really the complexity that you want to understand. Understand in order to understand this, model this behavior of how the hyperparameter variation affects the performance of your neural network. More concretely, you can define your loss function in regression. You can have the squared loss, or you can convert it to a utility function. So your y here are the true labels or true regression values. Tau alpha wx is basically what your neural network computes on your data set X when you set hyperparameters alpha and w. So this function sort of captures how the entire range of network behaviors as you vary both alpha, w, and x. And there is a reason why we care about w, because maybe when you apply the neural network, there's only going to be a fixed w that actually appears, that will learn w. But the w that you learn is affected by the hyperparameter alpha. So in order to understand what you're going to learn, you have to consider this broader function which captures the behavior of the neural network as a function of both the hyperparameter and the parameter.
I'm a bit confused with supermode W here. I mean, shouldn't you be looking at how you learn W rather than supermode?
So that is the aspect we are assuming. You learn. So one motivation for this could be like in the current neural networks, you think of achieving zero training error, right? So there is a bunch of ways in which you can achieve zero training error. And let's say we sort of black boxes. We assume somehow magically you have that best W.
This means zero training error?
In this case, this doesn't exactly mean best training error. This just means the loss on any data set.
So you mean training loss, or?
Yeah, and it could capture training loss. It could, for example, capture training loss. It could also be the best, depends on what you're interested in. So it could also capture the validation loss. You would typically care more about the validation loss, right? But this is still a meaningful definition for the training loss. For example, if you're caring about this multitask setting where there are multiple tasks, so you might even care about the training loss. You're trying to use a hyperparameter on a new unseen task.
I'm a bit confused because if you really just care about the training loss, why just consider it as a parameter? You should just like, I mean, if I have some parameter and really just I want to set it to minimize the training loss, it's not a hyperparameter. It's just one of my learning parameters. I'm just optimizing over W and alpha. Usually when I think of a hyperparameter, it's because, I mean, it's some high-level problem. Like I'm tuning it not in order to optimize the training loss, but in order to optimize the test loss or the runtime or something like that.
Right. So yeah, exactly. So F, we don't. These are examples of like accuracy are examples. You could also think of other utility functions. So we're trying to capture all the behaviors that the network could exhibit.
I'm still trying to understand in what situation do I care about the soup, but then it's still like meaningful to think about it as hyperparameter tuning.
Right. So one example, yeah. So if you care about validation loss, right? So let's say we care about validation loss, and let's say we have a magical algorithm which gives you the best weights on
best validation loss?
On the training set.
Oh, the training soup. Okay.
It gives you the best. Yeah.
So it gives you the ERM. Okay, but then that's not the soup then. No, you don't care about the soup then. You care about how the ERM does on the validation, which is different than the soup of the validation.
Right, but the range of behaviors of the network, so you learn a certain range of networks as you vary W. Yes, you learn a certain range of a certain class of networks, right? And you care about how this, so if you care about the validation loss, your networks, once you learn a fixed network in terms of alpha and W, that for example, the soup. The reason we care about the soup is, we assume that there is some algorithm which gets you the best W, right? We have an ERM oracle, let's say.
ERM is not, okay, we're going around in circles. ERM is not soup of the validation error. I mean, seems to be crucial here, but it seems like we're just going around in circles.
Right. Okay, so the example, so we care about, there are examples where we care also about just the training error, which is the transfer learning example, which I talked about. You might care more about the validation error if it's, if you're talking about this cross-validation in a single task.
So can I think of this so we're going to assume that we have an oracle. So for any given hyperparameter, we have an oracle that can say, okay, what is the best for whatever our measure is? That's F. And so F is sort of incorporating our kind of the goodness of W, and so we just have an oracle for that. That ideally we would have an oracle that would take in W and alpha together. We don't have that kind of oracle. Right. We have an oracle that you've got to give it an alpha, and then it'll find you the best W, and that's according to F. And so F is, F is the thing that we are caring about right now, and we have an oracle for F. That you got to feed it, you got to give it the X, you got to give it the alpha, then it'll find you the W. So that's kind of.
Yeah, that's right.
So I'm happy with this being a well-defined mathematical setting.
Yeah.
But I'm a little. You mentioned that you're not so much interested in the learning rate, you're more interested in things like parameters of your non-linearity, right? Your
right.
signal.
Yeah.
But in that example, I mean, the reason we can't just fold the learning rate in is because the learning rate is a parameter of the optimization algorithm.
Right. That somehow inside that soup process,
but a parameter of a non-singularity of a non-linearity is something we could do gradient descent on.
Exactly.
So I'm a little confused about why is alpha. What do we mean when we say alpha is a hyper? I mean, why are we prevented from folding alpha into W?
Right. I mean that's a great question. So that's a great question. So alpha we're treating alpha as a hyperparameter and not W as a hyperparameter. you could. So when I said like there are these gradient-based methods which do hyperparameter optimization, they are able to treat both alpha and W as a hyperparameter, right? So like that is one of the techniques. But we don't have principal guarantees for like whether you're selecting the best alpha there. There is no idea of like sure you select it.
So maybe the way you want to view it is that if you have it's confusing to think of this as a hyperparameter. It's really just a parameter. You have your hypothesis space or your parameter space or whatever you want to call it, and you're decomposing it to some part where you're saying you already know how to optimize, and another part you don't want to know how to optimize, but it's somehow small, and you're going to get guarantees on optimizing with respect to the second part, assuming you can already optimize with respect to the first part. Is that how to think about this?
Yeah.
Well, I think there's one other aspect to it, which is that later you're going to be given a new, this is for a single X so far, given a family of X's, right, you're going to want to be using the same alpha for all of them, but different W's. So the idea would be that you're going to, the alpha is then going to be hard-coded into some system that on any new instance you're going to train up the W, but the alpha is the thing that is not trained at training time. I think.
Yeah, no, that's correct. So someone is writing code for designing a neural network for a specific application like the Amazon application, then your data set, you might keep getting new data. So you want to figure out what your best alpha is. So you keep getting new data, but you retrain your network, but you will fix your alpha after some point. You don't want to keep retrying alphas once you know, you have a sense of what is the best. Alpha, in some sense, here captures the network architecture. So in some sense, if you've captured the network architecture, can you... Right. I mean, so you can say in some sense this is arbitrary, right? So this decomposition in between what you call a hyperparameter and parameter is arbitrary, but the distinction really comes in like what you are fixing during training, what you are updating during training. Okay. I'm happy to chat more. I think this is definitely a crucial part of. There's a lunch if you want to like keep discussing this more, because we can get into more examples here. Right. So let's start with the now this data-driven formalism, right? So we consider a specific aspect of this problem. We start looking at the learning-theoretic complexity of tuning this hyperparameter. So you want to output at the end what our goal is to output some tuned hyperparameter, which performs as well as the best hyperparameter that you could have selected. So you have this distribution from which your data sets are coming. You want to select a hyperparameter A hat, which is close to alpha star with high probability as you draw problem instances from that distribution. So this is the instantiation of the classic machine learning theory framework, but to this problem of hyperparameter tuning. And ask the first natural question to ask is like how many samples are enough to give a guarantee of that you'll be able to learn a good hyperparameter if you work with those many samples. If you try to do any sort of ERM with respect to alpha on those samples.
Quick question. So should I think about X as a data set and D as a distribution over data sets?
Yes.
I see. So we want to find one hyperparameter that's going to work on a family of data sets.
That is correct. Okay. So we just recall, people, if you're not already familiar with this, we recall this thing from statistical learning theory, which says you have this. If you want to find out the sample complexity, you want to look at this function class, which maps your input instances to the value of the utility function as you vary the hyperparameter. So, and there is the notion of complexity, the pseudo dimension, which mathematically is the maximum size of the data set for which you can use some thresholds such that you get all above-below patterns with respect to those thresholds. So there are 2 to the n possible patterns which this function can achieve on your input instances. As you vary your parameter alpha, you should be able to achieve all the above-below patterns. So your function class complexity as you vary the hyperparameter is complex enough to shatter this instance. So the larger the instance you're able to shatter, the larger the dimension, the larger the complexity of the function class. So this is all classic learning theory stuff. And you also have this result which says, if your pseudo-dimension is finite, then you can give an upper bound on the sample complexity in terms of the pseudo-dimension. All right, so then the rest of the goal of here is to actually bound the pseudo-dimension, understand the complexity of this function class and bound the pseudo-dimension. So recall their utility function was taking this soup over W for fx alpha W. We have this parameter dependent utility function. Now we, in order to actually give a bound on U, we will work on something called the parameter dependent dual. So here, what we do is we fix actually the input instance. We fix the input problem instance x, and we study the behavior of this function as you change both the parameter and the hyperparameter. So that is what we mean by the parameter dependent dual. And there are well-studied cases where this parameter-dependent dual has a nice piecewise polynomial structure. So for example, if your activation functions are like piecewise linear or piecewise polynomial, then this parameter-dependent dual will be a piecewise polynomial function where you can bound the degrees in terms of the number of layers and nodes in your neural network. So yeah, you can give you essentially will have boundary functions which are polynomials in both alpha and W. You will have you can partition the domain into pieces, and within each piece, the network's behavior will also be polynomial, and you can bound the degrees of both the boundary functions and these piece functions. So yeah, so ultimately, what we care about is essentially this very general question of taking this, finding the pseudo dimension of this function class, where you start with a piecewise polynomial dependence on both the parameter and the hyperparameter. You decide something is a hyperparameter, and you take this soup over, you train out the rest of the weights, and then you will you want to study this modified function class which involves this optimization problem. So this is a different function class which doesn't have a very clear structure. You don't even have a closed form of what that function class will be. Okay, to give some visuals, you have this nice picture where you have these blue and green boundary functions which are both polynomials. Then you have they would decompose your parameter and hyperparameter space, the combined W times alpha space, into a bunch of pieces, connected components, and within each piece there is some polynomial behavior. So within each piece, the network's behavior is some bounded degree polynomial. So that's you can have a different polynomial in different pieces. And our goal is to bound the pseudo dimension of this U function. So in order to do that, we are interested in this dual function. So there is this picture which captures the dual function, which shows the dual function on the left, which is doing this maximization over W. So you get this this function in the red, which is this piecewise structured function where the pieces you don't even know the closed form of these pieces, but we hope to give some sufficient structure on these on this U star X in order to give this bound on the pseudo dimension that we care about. So yeah, just to reiterate what I just said. So yeah, to bound pseudo dimension of U, it is sufficient to bound the number of discontinuities and number of local maxima in this U star X alpha. So yeah, your initial guess might be that if everything is piecewise polynomial, when you take the max is the final thing. Also piecewise polynomial, turns out it's not. It's easy to construct examples where this U star function is not piecewise polynomial, but it still has, and it's not always even possible to get a closed form for this. But still we'll be able to say something nice about this function. So that's the main challenge here. The final result that we have is that...
Just going back, so just make sure I'm reading this right. So that one more, just as yeah, good. So for any given alpha, you're finding the optimal W. That's the lines kind of on the horizontal, and then the value, the actual utility to get that's
from the surface there.
So that's basically just taking this picture and like just mushing it against that wall to get the maximum.
Yeah. So the red lines at the bottom here are these maximums. So the maximizations could either appear on the boundary or they could also appear in the interiors of these pieces somewhere, because these are polynomial functions. The boundary maximization can happen anywhere. I'll go into more detail about this picture. This will come up again when I give a proof sketch. But yeah, exactly as now. So once you find out where the maximum is, then that essentially gives you the U star function. Right. So this is the final result that we have. So we can give a bounded pseudo-dimension of U in terms of things that are easy to compute for any neural network problem that you're working on. If you can give a bounded number of connected components, the number of boundary functions, the dimension of the parameters, which is just the total number of weights in your network, and the maximum degree of both these boundaries and the piece functions, then that our result automatically gives you a bound of the pseudo-dimension of U. To give a concrete instantiation, so if you have this neural network with L layers, and each layer you have some number of parameters, so there are a total of W parameters, and there are K nodes. At each node you have an activation function, which involves this linear interpolation of two piecewise polynomial activation functions. So your O1 and O2 are piecewise polynomial with maximum degree delta and at most p pieces. And you have, so you assume you have t samples in each problem instance. All right, so this is the within instance. So you have, these are not IIDs. These are, you don't even assume the data set themselves are IID. Only the problems drawn from the distribution are assumed to be IID. But there are t samples within each data set. So with all these parameters, you can plug into you can compute n, m, d, and delta, and you can give a bound of the pseudo-dimension of the function class that we care about. In terms of the number of layers, number of weights, the degree of the activation function, pieces of the activation function, and so on. So this is the concrete instantiation. We have another example for graph neural networks in the paper. But let me move on to the cool stuff, which is the new techniques that we develop in the process of mathematically analyzing this pseudo-dimension. Right, so this is the high-level goal. You want to analyze the piecewise structure of this U star X alpha function. We want to bound the number of discontinuities and the number of local maxima. And turns out there's a lemma you can write which says that these are sufficient quantities to characterize this above-below behavior, the worst case above-below behavior that the family of functions can exhibit with respect to the shattering that we care about. So so here are the key steps. I'll go over each of them in detail, but just to give a feeling of what's going on. You start with reducing the problem. So you have multiple pieces. You have this piecewise polynomial with all these pieces and different. You reduce the problem to you can reduce the problem to a single piece, but it's challenging even within a single piece. So within a single piece, you identify all possible locations of the best weight, and those can appear either on boundaries or in the interior. If they appear in the interior, they must correspond to some kind of derivative with respect to the weight being 0. Right, so some kind of derivative curves or boundaries. And one thing we are able to show that, roughly speaking, these locations correspond to one-dimensional manifolds. Once you have these manifolds, you can decompose them into what we call monotonic curves, which I'll get into, which is one of the cool properties of the proof. And then once we have these monotonic curves, you can give a bound. And there's another step you need to give a bound in the number of local extreme of your polynomial piece functions along any of these curves. So I'll go into each step in a little bit of detail. So the first step is actually pretty simple. So you start with these multiple pieces. You have these two polynomial boundaries. You can partition your space into intervals based on the alpha endpoints of the pieces. Right. So you take the endpoints for each piece, and you can get intervals where there's a fixed set of pieces for each value of alpha within the interval. And then given a fixed finite set of pieces, we can also show that it's sufficient. Like suppose you have the fixed set of pieces for an interval, let's say alpha 2 to alpha 3. We also show that it's sufficient to analyze one piece, and you can analyzing one piece, you can put together easily the discontinuities and local maxima across multiple pieces. So essentially, we've sort of reduced this problem to a single piece with polynomial boundaries, and within the piece there is a polynomial function. This part is not very hard. Then the next step is to see where the best steps can be located. So they can either be at the boundaries or some interior stationary points. This corresponds to intersections of some algebraic varieties or these polynomial equations, solutions of these polynomial equations, where you take the derivative with respect to each possible weight and sort of intersect all those curves, all those hypersurfaces. And so there is some intuition why this should be one-dimensional. right? So because you have d-dimensional hypersurfaces in R d+1, and you're intersecting d of them. So for the derivative curves, it's relatively easier to see why this should roughly be a one-dimensional manifold. But we also care about these boundaries, and there's something more tricky going on in the boundaries. We care about intersections of any subset S less than equal to d of boundaries. So because funny things can happen when you're at the intersection of, in high dimension, you can be at the intersection of multiple boundaries, and the function can have local maxima and minima along the edges of these these boundary surfaces. So what we can still do here is we can set up a Lagrangian, and this Lagrangian tries to optimize this function along the intersection of any subset S of boundaries. So you can take and you essentially get a manifold, one-dimensional manifold in a higher dimensional space where it's no longer just d plus one dimensional, it's essentially d plus s plus one dimensional space where you also have the Lagrange multipliers as the variables. This is sort of tricky, but also like a cool high-dimensional projection trick, which gives a neat structure in higher dimensions. And once we have these one-dimensional manifolds, we can we decompose them into monotonic curves. So essentially, you consider all the extreme points with respect to alpha. You can break down your functions based on that. Break down these manifolds based on that. So essentially, the monotonic curve is just saying along any fixed value of alpha, you will have a fixed set of monotonic curves that you intersect with. There's a monotonic curve, and so that each monotonic curve, the alpha equal to alpha zero hyperplane will only intersect at most a single point. So these functions are these are sort of as long as your set of monotonic curves is fixed, the function must be at least continuous. Your U star alpha must be continuous. It can still switch back and forth sort of between these monotonic curves. And can experience local minima and maxima, but the function itself is going to be continuous. This gives this step 3. By this point, we are able to bound the number of total possible discontinuities in here. Because across these extreme points of these monotonic curves, the function can still jump because you're moving, potentially jump. Finally, we use this. Apart from discontinuities, the next step was to bound the number of local maxima. So here we use Lagrange multiplier and Bezout's theorem to bound the number of local extrema. Again, these are there are some people from with the algebraic geometry background who were interested in this aspect, so I put this detail here. But this from the earlier talk at Chicago. So there is this curiosity of how do we use Bezout's theorem from algebraic geometry. So the idea is you have these monotonic curves, right? So you have this monotonic curve across which your optimizing W can potentially occur. Now you want to find where your polynomial objective can have local extrema. So you can essentially just say you have this function, you have this curve C, which is the intersection of polynomial equations. You have this polynomial objective, and you set up a Lagrangian. All the derivatives of the Lagrangian are also polynomials. So which allows you to apply Bezout's theorem to give a bound on the number of points, number of local extrema along these monotonic arcs. Again, it's fine if you don't get this detail immediately. It's just if you have some algebraic geometry background, it could be interesting to understand this. But final thing, we put everything together. So the discontinuities that can possibly occur in U star alpha, we can bound them by these partition into regions which have a fixed set of monotonic curves. So the regions where your alpha equal to alpha 0 intersects in a fixed set of monotonic curves, and then you can also bound the local maxima using that last step. And finally, we have this lemma which puts everything together. So we have V1 discontinuities and V2 local maxima in any function for any fixed instance x. Then you have a bounded pseudo-dimension in terms of the number of discontinuities and local maxima. So this is basically the full recipe of the proof. So I have a little more time. I'll spend that to give a broader context for data-driven algorithm design and how this whole thing fits in into this, this broader suite of tools and framework that we've developed that goes beyond just deep network hyperparameter tuning to other machine learning problems and even beyond machine learning to just algorithm selection. Right. I'll start with some motivation for why we care about data-driven algorithm design. So, especially in machine learning, you have so many, new applications across domains popping up. More and more people are adopting machine learning and new applications showing up every day. At the same time, there's also an explosion in the research in machine learning. So again, this is a slide I've used several times, but I just like it so much that I repeat it in every presentation. So there is this, you see the growth in the CS publications and archive overtaking math and over the last few years. And even within CS, the learning, computer vision, and computational linguistics are the three top dominating fields. So you see new algorithms essentially in machine learning for different aspects every day. Essentially, now the question is these two trends are sort of reinforcing each other. There are more powerful algorithms, and there's more applications, and more applications need more algorithms, and so on. So there's a whole bunch of new algorithms with hyperparameters and everything. But at the same time, there's this more worrying trend, which is like, in what sense are we truly automating, right? So we need more and more data, or and more and more hyperparameter tuning. There are also other concerns, like whether these things are trustworthy. We are deploying them everywhere, but we don't know how trustworthy they are, how interpretable they are. So these challenges are also more magnified. Right. So data-driven algorithm design sort of tries to, essentially, in this context of machine learning, it tries to use machine learning to solve these challenges that are posed by increased adoption of machine learning across domains. So the idea is you have algorithm families, including these hyperparameter-based families, or you can even interpolate good heuristics. You can always generate new families, which you believe that there is some good algorithm within the family that will work well. Right, so classic example, elastic network linear regression, which you see in Stats 101, has these L1 and L2 regularization hyperparameters, and by getting the best hyperparameter, you can hope to work well across. By tuning them to specific data sets, this becomes a much more powerful algorithm than an algorithm which doesn't set these hyperparameters. And the other thing you see is, like, especially if you're working in a fixed domain, you see repeated problems or updated data sets within that fixed domain. And there can be a range of models in which you can set this. So in this work, we talk about this IID setting, but you can also think of, like, you have a new data set in some online fashion each day. You can also frame this as an online learning problem. So you have this whole range of settings. And the other, so with this framework, what you want to essentially do is you want to study algorithms as a concept space. So that's this whole idea of data-driven algorithm design is you have these concept space like linear separators and all the things that you use in classical machine learning. But here we're treating the algorithm families themselves as concept spaces, and your points are essentially your data sets or input instances on which the algorithm is going to be applied. So the algorithms, they present novel technical challenges in terms of both the complexity of the hypothesis class is pretty hard to analyze. You have sharp transition boundaries. As you change some of these parameters, there can be sudden jump in the algorithm's behavior, which is even worse as you go to higher dimensions. And you run into optimization problems, which no longer correspond to these nice, smooth, convex situations. You learn to highly non-convex and even non-smooth optimization problems. So you need more technical advances to actually solve this. I'll give a couple examples where we have nice set of results in machine learning, tuning parameters in machine learning. So you have this graph-based learning where each day you see a new data set. You're doing semi-supervised learning, so you don't see all the labels, but you maybe construct a graph to extrapolate the known labels to the unknown labels. So things which are close by in the graph. So you can use like a min cut or a soft min cut to partition the graph, and then you can predict. You can give predictions based on which cut you land. So you can extrapolate the known labels to the unknown labels. The question this technique has been known for more than 2 decades, but the question that has not been addressed is, like, how do you even set the initial graph, right? So that is kind of like a black magic. So this our techniques allow you to actually design this graph. You know, you can have these Gaussian RBF kernels or even simpler families. You can how do you set the weighted edge weights before you even start doing this min-cut procedure. So we give tight upper and lower bounds, the learning-theoretic complexity of tuning those hyperparameters. We also do give online learning algorithms which achieve no regret. So there are these interesting algorithms which which you essentially find the set of min-cuts for not just a single parameter, but as you vary the hyperparameter, you can use a primal dual style algorithm to compute the min-cuts as you vary the set of hyperparameters. Another example which received attention is this decision tree work that Abram mentioned at the start of the talk. So here, one cool thing that we're able to do is like there are these sort of distinct approaches people know for tuning hyperparameters, like for tuning these learning the decision tree, which include like entropy or gene impurity or even other criteria which satisfies a concavity property. And it's not clear if you're given a data set, essentially the practitioner will try out all these three and see which one works best and just start using it. But is there a principled way of selecting these hyperparameters? And what you can do is we propose a novel family which sort of unifies all these different sort of so far thought of as distinct heuristics into a single parameterized family, and now you can sort of automatically select not only between these three criteria, but in a much more powerful family which sort of interpolates between all of these. And then we can do this technique in a bunch of different settings. And the general idea, again, almost throughout, is to be able to analyze how the behavior of the algorithm changes as you vary these parameters. That's sort of the core crux, and that's both giving structural properties for that behavior, but also once you know that behavior, maybe how do you solve this optimization problem to find the best parameters? Those are sort of the interesting questions that pop up when you start looking at this data-driven lens for hyperparameter tuning. So let me summarize since we're close to the end. So we have hyperparameter. So the understanding is like this hyperparameter tuning is poorly understood, and yet is of critical importance because and why is it a must? Why is it a sort of unavoidable challenge? It's because machine learning works on data, right? So your data will always come from some domain, and you must always want to use your algorithm, the best possible version of the algorithm which works on the domain-specific data. There's a lot of these applications are so high stake that you really must find the best, most optimal tuning for the data. Otherwise, you don't even care about the algorithm if you're not able to, optimize or tune it. So essentially, the magic of machine learning relies highly on this ability of being able to tune hyperparameters specific to data, and the current practices for doing this, unfortunately, require incredible amounts of compute, engineering resources. There is growth in it requires more and more domains start applying machine learning. There's a growth in demand for a number of engineers you need to apply these machine learning techniques to these domains. But all of this effort is somehow super unprincipled and super sort of inefficient because we don't really understand how the behavior of any of these algorithms vary with. So we're only beginning to understand how the behavior of the algorithms actually change with these hyperparameters, how much data we really need, or how much tuning do we actually need to give anything, any provable guarantees. In the specific context of deep networks, we formalize this data-driven model hyperparameter tuning, where which naturally captures this transfer across tasks. We analyze techniques which for analyzing the pseudo dimension, by using geometry of the dual utility function. In particular, it allows continuous hyperparameter selection, which a lot of previous techniques don't even handle, like grid-based or bandit-based approaches typically work with discrete hyperparameters. And we examine the structure of U star, your dual parameter, your dual function that you care about, by analyzing this parameter-dependent dual. So because we know structural properties about it, and that's sort of the key technique here. It feels like this particular overall structure can appear in other problems. You can have parameters and hyperparameters, and you can try to do an optimization over parameters of that particular aspect. Even though it appears very frequently in machine learning, we hope to see it other places. But even for a single hyperparameter, we have concrete instantiations where our current results apply, including this parametric ReLU example, interpolating pairs of piecewise polynomial activation functions, and designing graph neural network kernels. There are a bunch of open directions, so we definitely care about extending these results from one dimensions to multiple real hyperparameters, right? So even why just select a single activation function? Why don't select different activation functions for different nodes? That's a very natural, immediate question to ask, and it's just already fairly technically challenging to work out the case for a single hyperparameter. So you really want to potentially even more powerful techniques to work out the multiple parameter case. We focus on the statistical complexity, and in other works we worked out computational efficient methods, but that's usually in this data-driven field sort of lags behind. So and then there's a natural question of can you, so what we say is you can compute the best hyperparameter by taking all your samples from your data set given the sufficient number of samples, but how do you actually find that best on-sample hyperparameter is an interesting question. Still, we don't have algorithmic answers. We only have sort of learning-theoretic answers at this point for this problem. In other cases, we have, like, when the piecewise structure is nicer, we have some algorithmic answers as well. And beyond, the other question is beyond piecewise polynomial structure. People care about more complicated activation functions. This seems like a relatively simpler question. Maybe include things like sigmoid and other activation functions. There's properties like Bezout's theorem which apply to piecewise polynomial cases, but there might be natural extensions to other natural classes of functions. We haven't worked out the online hyperparameter tuning setting here, but that's again another natural question because the IID assumption of relatedness of your different tasks might be too strong in certain cases. So there's can you think of more settings which require fewer assumptions on the data distribution being identical or independent. Fewer assumptions there, and finally, we do expect other applications. Because our overall mathematical tool is fairly general. You have parameters and hyperparameters. You max out on the parameters. So there is this whole idea of bi-level optimization where the theoretical understanding is sort of limited to just very special cases like convex functions. But the setting we are studying is sort of inherently piecewise polynomials are highly non-convex. So at the very least, we can give learning theoretic guarantees for these non-convex settings. It's interesting to see what this implies for this optimization literature. And we consider only feed-forward networks. We also think, there might be interesting, cool questions for other neural architectures or algorithm families people care about. That's all I have. Thank you so much for listening.
So kind of, it's of interest. So this formal distinction between hyperparameters and parameters, right? So in some sense, if you were able to push everything into parameters, in some sense, that's great. If we could really optimize, right, then ideally in every instance we would optimize everything. And I guess, so I guess formally the hyperparameters are things that it's too expensive to optimize on instance, and so we're fixing them, and those are the things we're trying to figure out over multiple instances, and then and then they're just so. Let's see. I guess. So what am I trying to ask? So so one reason you might do that was just because it's what you can actually optimize over. Like the weights are things we have algorithms optimize. We just don't have algorithms that optimize very well over these other things. And then another aspect has to do with maybe statistical complexity. And it could be that maybe we think we'll get better generalization if we pull some things out and don't actually optimize over them in the problem itself. I wonder if your work gives some sense about that. like one thing I find interesting and surprising is that actually sometimes your functions can get more complicated if you take them and write them just as functions of the hyperparameter.
Right.
Like you project out the parameters by taking the soup. And now you get even more complicated because you're taking a max of some stuff, and the max of some stuff can be more complicated than the stuff you're taking the max of somehow. But I wonder if you have some sense of, if like whether there are things that, gosh, these things maybe ought to be hyperparameters because they're really causing a lot of problems statistically, or the other way around. Okay, that's a fuzzy question.
Yeah, no, that's a great question. Again, so these distinction between parameters and hyperparameters is very true. We care about identifying what we want to call as hyperparameter in the first place. There can always be techniques for optimizing things. In some sense, one aspect that we are capturing is we can say something more principled in some sense about this hyperparameter selection. So for the weights, we let's say we are we sort of assuming we tune these weights to optimality. So maybe there's some decomposition of your problem where there's this hard aspect which if you can, the best hope is to just do some sort of approximation, and maybe there are some hyperparameters where the structure turns out to be nicer somehow, and you can do this optimization more easily. Again, that you have to start analyzing the structure to be able to tell that. But again, it's definitely very much possible, as you say, like this structure is potentially more complicated than the original structure you started with. Why don't you want to tune both the hyperparameters and parameters on the same instance? And the belief, one of the reasons why you would want to do is that, it's when you're trying to tune both, it could potentially be, you want to compare the quality of how well you're able to optimize, how efficient you're able to optimize. Essentially, that's the main difference. So one way to further understand the significance of this work is to try to do these comparisons where you tune both of them simultaneously versus maybe one of them you're able to do perfectly and the other one you do use some heuristics because it's harder to optimize. Right. So that's one sense in which you could get a fairer comparison of what to do in practice. Right.
Any other questions? All right. Thanks.
Thanks.